Okay, let's be real. If you're feeling a little bit of panic about elasticity and material physics, just take a deep breath right now. We are going to transform all that stress into total mastery today. Welcome to your ultimate exam cheat code explainer. We've built this specifically to walk you through the core concepts, the absolutely essential formulas, and the exact problem-solving steps you need to go in there and secure a perfect score.
So here's our study roadmap. We are covering 6 key areas today: Hooke's law and springs, the fundamentals of stress and strain, the 3 elastic moduli, the stress-strain curve, a fully worked exam calculation, and finally, a rapid-fire practice quiz.
All right, Section 1, Hooke's law and springs, restoring forces.
Now, what's really cool here is how this actually visualizes Newton's third law in action. Whenever you pull or push a spring, displacing it from its normal, unstrained length, it pushes or pulls back, right? Well, that is called the restoring force. And for relatively small displacements, this whole thing follows Hooke's law. Hooke's law basically states that the restoring force equals negative k times x. That k is your spring constant, or basically its stiffness, and that super crucial minus sign, that just reminds us that the spring is literally always fighting against the displacement.
Moving right along to Section 2, stress and strain, measuring deformation.
Okay, the absolutely vital point here is really getting the difference between these two terms. They sound similar, but they are very different. Stress describes the actual forces causing the deformation inside a material. We calculate that as force per unit area, and it's measured in pascals. Strain, on the flip side, is the physical result of that stress. It describes the amount of deformation. It's just a fractional change, like, say, the change in length divided by the original length. Because it's a ratio like that, strain is completely dimensionless. It's just a pure number.
Listen, if you only memorize one single thing from this entire explainer, please make it this master key equation. Stress equals the elastic modulus multiplied by strain. In the low stress, linear region, deformation is directly proportional to stress. And that proportionality constant, that's the elastic modulus. Pretty much everything else we're going to discuss is just a variation of this one fundamental pattern.
Let's dive into Section 3, the 3 elastic moduli. Elastic constants. And this brilliantly illustrates our very first one, which is Young's modulus. You're going to use this when forces are stretching or compressing an object along a single dimension. Think of a steel rod or a vertical pillar. Whether it's tensile stress stretching the thing out or compressive stress squashing it down, you are dealing with a change in length. Oh, and a high Young's modulus, like you'd see in steel, simply means the material is incredibly hard to deform. Next up is the bulk modulus. Picture a submarine diving deep into the ocean. It's getting uniformly squeezed by water pressure from all sides at exactly the same time. The bulk modulus measures an object's resistance to this all-around compression, which obviously results in a change in volume. Now here is a massive exam tip for you. The bulk modulus formula always includes a minus sign. Why? Because an increase in pressure causes a decrease in volume, and that minus sign just makes sure the final modulus remains a positive number.
Finally, we've got the shear modulus. Now this one is entirely unique to solid objects. Fluids literally cannot sustain shear stress. Shear happens when 2 equal and opposite forces act parallel or tangentially to the surfaces of an object. Think about putting your hand flat on top of a thick textbook and pushing sideways. The pages slide relative to each other, right? That lateral shift right there is shear deformation.
All right, let's lock this in for your exam with a high-yield summary table. I want you to notice how all 3 formulas share the exact same structural DNA. Modulus equals stress divided by strain. Young's deals with perpendicular force and length, bulk deals with pressure and volume, and shear deals with parallel force and lateral shift. If you just master the core concept, you really don't have to blindly memorize 3 totally different formulas. Onward to Section 4, the stress-strain curve, mapping deformation.
Take a really close look at this curve. It's a perfect map of how a material behaves as stress increases. Notice how it starts down at 0 with a perfectly straight line? That is where Hooke's law applies. But as you keep piling on the stress, the line begins to curve, eventually hitting a peak, taking a little dip, and finally ending abruptly when the material physically snaps. For your exam, you absolutely have to memorize these critical plot points. Point H is your linearity limit. Past this spot, stress and strain are no longer directly proportional. Then we hit point E, the elastic limit. Guys, this is the point of no return. Up to E, if you remove the stress, the material bounces back perfectly to its original shape. But the second you cross that E boundary into the P zone, the material suffers irreversible, permanent plastic deformation.
And finally, that ultimate stress right at the end of the curve is the fracture point, literally where it breaks. Okay, Section 5, Exam Calculation. Multi-step problem. Look at this classic problem. We've got a 10,000 Newton sculpture sitting on a 6-meter granite pillar, and we need to find the stress and strain exactly 3 meters down. Now, instead of panicking over a giant wall of numbers, let's just scaffold the math. Step 1. Find the volume and mass of just that top 3-meter segment of the pillar, using the density they gave us. Step 2. Calculate the total downward force. We do that by adding the weight of the sculpture to the weight of that top granite segment. Step 3. Divide that total force by the area to get your compressive stress. And finally, divide that stress by granite's Young's modulus to find your dimensionless compressive strain. Just show every single one of those steps clearly, and I promise you will get full marks.
All right, home stretch. Section 6, practice quiz, active recall. Let's see what you've got. Question 1. Think about a stretching elastic band, or maybe the compressive force on that pillar we literally just calculated. Which modulus is at work here? And the answer is Young's modulus. It perfectly describes those one-dimensional tensile or compressive forces that end up changing the length of an object. Okay, question 2. Imagine that submarine we talked about, deep underwater, getting squeezed uniformly from every single direction so its volume shrinks. What's that one? You guessed it. That is the bulk modulus. And remember that crucial exam tip we went over? The minus sign is just there to keep the final value positive, since the volume physically decreases under all that intense pressure. All right, final question. Remember, a fluid absolutely cannot sustain this specific type of stress, but if you push tangentially across the top of a solid block, it shifts. What is it? Nailed it! It's the shear modulus. This one deals strictly with those parallel, sideways forces that cause a lateral shift in solids. Well, you are now fully equipped to conquer this exam. Always, always remember the golden rule. Stress equals modulus times strain. Now, take a look around the room you're sitting in right now. Look at the walls, the ceiling. What specific material properties do you think are keeping the roof over your head from permanently deforming under its own weight? Stay curious, keep studying smart, and you are absolutely going to ace this test.